Welcome, sleepy friend, to another quiet journey with the Dodo Scientistry. Whether you're here to learn, unwind, or simply drift into a peaceful doze, you're in just the right place. Tonight, we'll be following a gentle trail of moonlight across the sea, exploring how the moon, yes, that glowing pebble in the sky, quietly tugs at the oceans below. It's a slow, steady pull, not unlike the way your eyelids might start to feel just about now. Before we set sail on this lunar voyage, I'd love it if you gave the video a little like. It helps this cozy corner of YouTube reach more fellow wanderers. And if you feel like joining me for more starlit science in the future, tapping that subscribe button is always appreciated. If you're feeling extra chatty before this news kicks in, let me know in the comments where you're watching from and what time it is in your part of the world. It's always a joy to see this little sleepy community stretch across time zones. Now, I'll do my best to keep things soothing and not too riveting, but if you do find yourself lying awake thinking about tidal forces and orbital mechanics, well, at least you'll have some solid science to ponder while the moon does its thing. So settle in. Let the blankets wrap around you like warm sea foam. Take a deep breath, and let's begin. Underscore 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 underscore. Picture this. A beach at dawn. The sky is barely blushing with light. The wind is whispering, and the waves are slowly creeping up the sand like they're stretching after a long night. It's peaceful, rhythmic, almost like the ocean is breathing, in and out, in and out. That's the tide. Quiet, constant, ancient. But beneath this calm ritual is a story of immense invisible forces. A kind of planetary choreography that's been going on for billions of years. And the star of the show? Our very own moon. Tides, in the simplest terms, are the regular rise and fall of sea levels across the globe. But they're not quite as simple as water sloshing back and forth. They're not caused by the wind, or passing ships, or the ocean getting bored and deciding to move around. They are the result of an intricate gravitational dance between the Earth, the moon, and the sun, a cosmic push and pull that shapes the very rhythm of our planet. Twice a day, every day, the sea retreats from the shore, and then returns. This is something so regular, so dependable, that humans have been tracking it for thousands of years. Ancient fishermen in China and Mesopotamia planned their harvests by it. Medieval monks timed their prayers to it. Entire cities have been built, and sometimes lost, because of it. But why does it happen? Why does the sea keep coming and going like it's late for something? To understand that, let's imagine the Earth not as a solid ball, but as a water balloon wrapped in a thin layer of land. Now picture the moon, silvery, steady, and quietly determined, pulling on that balloon with its gravity. It's not a yanking, dramatic pull, but a subtle, continuous tug. The moon's gravity pulls the ocean toward it, creating a bulge of water on the side of Earth that's facing the moon. That's our first high tide. But here's where it gets weird, in a fascinating bedtime story kind of way. There's a second bulge on the opposite side of the Earth, the side facing away from the moon. Wait, what? How can the moon be pulling water toward it and creating a bulge on the far side? This is one of those moments where the universe seems like it's showing off. While the moon's gravity pulls water toward it, the Earth itself also gets pulled slightly toward the moon. But the water on the far side lags behind a bit, like a sleepy cat refusing to follow the rest of the household. This creates a second bulge, not because the moon is pulling the water away, but because it's not pulling it as hard as it pulls the Earth's center. That gentle difference in force, what scientists call a tidal force, stretches the oceans into a sort of oval shape. One bulge faces the moon. The other faces away. As the Earth rotates beneath this watery distortion, different parts of the world move into and out of these bulges, experiencing high and low tides in a rhythmic pattern. It's gravity's quiet masterpiece. And all of this is happening constantly. Even as you lie there now, warm under the covers, the moon is pulling gently at the oceans. Somewhere, a beach is being uncovered. A boat is rocking a little lower in the harbor. A crab is deciding whether it's safe to come out from under a rock. The time it takes between high tides is about 12 hours and 25 minutes, just a little over half a day. That's because the moon isn't standing still. As the Earth rotates, the moon is also orbiting us, moving a little further along in its path every hour. So each high tide is slightly delayed compared to the one before it. If you were to live by the coast and mark the high tide times every day, you'd notice they're always shifting, arriving later and later by about 50 minutes each day. The moon is nothing if not fashionably late. Now, not every place on Earth experiences the same kind of tidal rhythm. Some places get 2 high tides and 2 low tides each day. This is called a semi-diurnal tide. Other spots might only get one of each, known as a diurnal tide. And in a few places, the tides are, well, irregular. These are mixed tides, where high and low tides vary wildly in size. It all depends on your location, the shape of the coastline, and the depth and contour of the seafloor. The ocean, like a cat, does exactly as it pleases, what it wants. But wherever you are, tides are an ever-present hum beneath the surface of life. They regulate ecosystems. They influence weather. They've shaped the migration of animals and the settlement of humans. And the best part? They're predictable. We can chart them years, even centuries in advance. Not many things in life are so reliable. There's something comforting in that, isn't there? That while everything else may feel chaotic, the sea still follows the moon, twice a day, every day like clockwork. Or maybe more like a lullaby, repeated softly over and over across the ages. And though we tend to think of the moon as distant and cold, it's hard not to feel a little affection for this quiet companion. It's been shaping Earth's waters since before the first fish wriggled into a tide pool. It's guided sailors, inspired poets, and even helped early Earth stabilize its spin. Without the moon, our days might be just a few hours long, and the climate far more erratic. We owe more to that rocky little sphere than most of us realize. So as you lie there, listening to the soft rhythm of this tale, think of the tides. Moving far away, unseen but certain. Think of the moon, turning its pale face toward us, whispering across space. And think of the water rising slowly against the shore, as it has done for billions of years. It is the ocean's breath, the Earth's quiet heartbeat, the moon's gentle pull. All of it part of the same ancient, elegant pattern. And it's still happening right now, even while you sleep. If you were to sit very still, so still that you could feel the thrum of your own heartbeat, you might begin to sense that there's something always happening around you. Something constant and invisible. Gravity. Gravity is the quiet force that tethers you to the ground, holds the oceans in place, and keeps the moon dancing around us like a curious little sibling. It's always there even when you're tucked under a blanket, sipping tea, or brushing your teeth in the foggy glow of early morning. You don't have to think about it. But tonight, we are going to. Because the tides, those gentle sways and sighs of the sea, are really just Earth's oceans responding to a very persistent invitation. Gravity's pull. Let's start with the basics. Gravity is the attractive force between any two objects that have mass. The more mass something has, the stronger its gravitational pull. You and I technically have gravity, although unless you're secretly made of neutron star material. You probably haven't had planets orbiting you lately. The Earth, on the other hand, has a lot of mass, enough to pull us all down to the surface and to keep the moon in orbit. So, Isaac Newton, the original apple-falling understander, first described gravity in the 1600s. He realized that the same force pulling that apple to the ground was also keeping the moon from flying off into the dark. The Earth pulls on the moon. But here's the twist, the moon pulls back. Not on the whole Earth equally, but especially on the oceans, which, being liquid, are a bit more agreeable when it comes to moving around. It's like a slow-motion tug-of-war. But the moon doesn't yank. It coaxes. It says, "Come here, just a little." And the ocean listens. The result? A bulge of ocean water on the side of Earth facing the moon. That's one high tide. And on the exact opposite side of the planet, there's another high tide, caused by something slightly more peculiar. Let's talk about that far side bulge for a moment. Because this is where gravity gets especially sneaky, while the moon pulls the water closest to it the hardest. It also pulls the Earth itself, rock, mountains, and all, just a bit less hard than the near-side water. The water on the far side, however, is barely feeling the moon's tug at all. So, relatively speaking, it lags behind. The result? Earth's mass shifts a bit toward the moon, and the far side's water seems to stretch away. Voila, a second bulge. It's not being pulled outward so much as left behind in the moon's slow embrace. This concept, differential gravity or the tidal force, is one of the most quietly elegant features of our physical universe. It's not just gravity pulling everything in, it's gravity pulling different things differently. That subtle imbalance is what sculpts the tides. To get a clearer picture, imagine stirring a bowl of soup while holding a slice of bread on the surface. As you swirl, the soup behaves differently depending on its distance from the center of motion. The bread might lag or surge too, depending on how you move. The ocean does something similar as Earth spins beneath the moon's gravity field. And yes, Earth is spinning. While the moon orbits us roughly once every 27.3 days, Earth completes a full rotation in just under 24 hours. So, from our perspective, it seems like the moon is gliding across the sky each day. But in reality, we're rotating beneath its gravitational pull. As different parts of Earth pass under the two tidal bulges, one facing the moon and one opposite it, we experience high tides. Between those bulges, the water levels drop, and we get low tides. It's a graceful, planet-wide pirouette. And it never stops. You might wonder, if gravity is so strong, why aren't the oceans simply flinging themselves at the moon? Why don't we see dramatic sloshing or waves leaping into space? The answer is balance. The same force pulling water toward the moon is also met with Earth's own gravity, anchoring the oceans in place. In fact, the entire Earth, moon system is held together in a stable, harmonious orbit, governed by the same laws of motion Newton figured out while presumably dodging apples. There's also centrifugal force at play, another ingredient in this planetary recipe. As the Earth and Moon revolve around their shared center of mass, which isn't Earth's center but a point slightly beneath its surface, this rotation creates a slight outward force. That force helps create the bulge on the far side of Earth, balancing out the moon's pull. The result? Two high tides, even though there's only one moon. But gravity isn't just playing games with water. It's also subtly deforming the Earth itself. The solid ground beneath our feet actually rises and falls by a few centimeters due to these gravitational forces. It's called Earth tide. And while it won't flip your coffee table, it's a reminder that nothing on our planet is truly still. The moon's role in this grand affair is central, but it's not the only actor. The sun also exerts gravitational force on the Earth. And though it's nearly 400 times farther away than the moon, it's also vastly more massive. Its gravitational influence is about half as strong as the moon's when it comes to tides. When the sun, moon, and Earth align during full moons and new moons, their combined pull creates higher high tides and lower low tides. These are called spring tides, not because of the season, but because the water springs farther than usual. When the sun and moon are at right angles, their gravitational forces partially cancel out, leading to neap tides, which are more moderate and subdued. So yes, the sun is involved too. But the moon, with its closeness and subtle persuasion, remains the tide's main conductor. Now, not all coastlines play along in the same way. If you lived on a perfectly smooth, water-covered Earth with no continents, the tides would be simple and fairly symmetrical. But we don't live on a perfect water world. We have coastlines, bays, islands, ocean ridges, and seafloor trenches. And all of these shape how ocean water moves. In some places, like the east coast of North America, the tides tend to follow a semi-diurnal pattern. 2 high tides and 2 low tides each lunar day, with each high tide roughly the same height. Elsewhere, like in parts of the Gulf of Mexico, you might find a diurnal pattern. Only 1 high tide and 1 low tide each lunar day. And in still other areas, the tides are a mixed bag, 2 highs and 2 lows per day, but of unequal size. The ocean, it seems, enjoys improvisation. The local geography plays a huge role. Narrow bays can amplify the tidal range as the water is funneled into a smaller space. This is what makes the Bay of Fundy in Canada such a tidal superstar, with high tides reaching over 16 meters. In contrast, the Mediterranean Sea, almost landlocked, has barely noticeable tides at all. It's like the ocean trying to tap its foot inside a tight shoe. Then there are amphidromic points, places in the ocean where the tide hardly changes at all. These are the quiet eye of a rotating tidal system, where the water doesn't slosh up and down so much as swirl gently around in a circle. If you were to float right over one, you might not even notice the tide was there. It's like the ocean's version of standing perfectly still in the middle of a merry-go-round. And just to keep things interesting, the Earth isn't a perfect sphere either. It's slightly flattened at the poles and bulged at the equator. That means gravity varies slightly across the globe, further tweaking the behavior of tides. So, the reason we experience 2 high tides per day isn't just the moon pulling at the water like a marionette. It's the result of a complex interplay between the moon's gravity, Earth's rotation, centrifugal forces, and the unique shape of our planet's oceans and continents. It's less like a metronome and more like a very well-practiced slow-motion waltz, one that's been going on for billions of years. And all the while, the water obeys. It shifts and surges, retreats and returns, flowing in step with the moon's persistent pull. It's a cycle so reliable that sailors have trusted it for centuries. So delicate that a changing coastline can alter its rhythm. And so subtle that you can stand on a beach, toes in the sand, and never feel the force pulling the whole sea toward the sky. But it's there, quiet, invisible, and constant. Like gravity. Like time. Like the moon rising in the east once more. If the moon is the headliner of the tidal show, then the sun is the special guest star, with a powerful voice. One that doesn't sing quite as often, but can still shake the house. While the moon is the main driver of tides, the sun also plays a crucial role, adding its own gravitational influence into the mix. Together, they create moments of dramatic crescendo and hushed interlude in the endless song of the sea. Let's begin with the sun's credentials. It's big. Really big. About 27 million times more massive than the moon, in fact. But it's also much, much farther away, about 400 times farther, to be precise. And here's where things get interesting. Because gravitational pull weakens with distance, the sun's effect on tides is weaker than the moon's. Despite its tremendous size, the sun only contributes about 30 to 40% of the tidal force that the moon does. Still, that's no small contribution. When the sun and moon work together, the tides grow bolder, stretching farther up the shore and plunging lower in retreat. These moments are called spring tides, though they have nothing to do with the season. The term spring here comes from the Old English word springen, meaning to leap. During spring tides, the ocean quite literally springs into action. Spring tides occur during full moons and new moons, when the Earth, moon, and sun fall in a straight line, what astronomers call syzygy. It's a fun word to say, and an even better concept to picture. Imagine the 3 celestial bodies aligned in space, gravity pulling from 2 directions in perfect harmony. The moon's tug and the sun's pull combine to create higher high tides and lower low tides. The tide's range increases, the contrast sharpens, and coastlines feel the difference. A full moon spring tide occurs when the moon is on the opposite side of the Earth from the sun. The sun pulls on one side, the moon pulls on the other, and Earth finds itself in the middle of a gravitational tug-of-war. Meanwhile, during a new moon spring tide, both moon and sun are on the same side of the Earth, pulling together like 2 teammates rowing in sync. In both cases, the result is a dramatic amplification of the tidal range, waves that reach farther and leave more sand behind. And then there are the neap tides, the ocean's gentle exhale after the excitement of the spring tide. These occur during the first and third quarters of the moon, when the sun and moon form a right angle relative to the Earth. Instead of reinforcing each other's gravitational pull, they partially cancel each other out. The sun tugs one way, the moon tugs another. And the ocean, caught between the two, shrugs and settles into a milder rhythm. Neap tides are characterized by lower high tides and higher low tides, more moderate, more restrained. The tide's usual drama is toned down to something more subtle and relaxed. In a way, It's the ocean taking a nap between high-energy performances. This monthly cycle of spring and neap tides repeats with the moon's phases roughly every 29.5 days. So, twice a month, the tides stretch higher and lower than usual. And twice a month, they mellow out. It's a reliable cosmic beat that the oceans follow like a natural clock. And what a clock it is. For centuries, sailors, fishermen, and coastal dwellers have lived by the tide charts, knowing that timing is everything. In the era before smartphones and satellites, spring tides could mean the difference between a safe harbor and a stranded ship. A fisherman in the 1700s might have set out knowing that a full moon meant deeper channels and stronger currents. An opportunity if navigated carefully, or a hazard if ignored. Even today, cities like Venice or London monitor spring tides closely. In Venice especially, spring tides combined with storm surges and rising sea levels can bring flooding, transforming narrow alleyways into waterlogged corridors. In London, the Thames Barrier, a marvel of modern engineering, stands ready to be raised during particularly intense spring tides, shielding the city from inundation. But it's not all potential peril. Spring tides are also moments of abundance. Along tidal flats and estuaries, they bring in rich nutrients and push them far inland, feeding delicate ecosystems. Crabs scuttle, birds feast, and plants rooted in salty mud breathe deeply, knowing their time has come. On a more personal scale, people still time their beach visits to the tides. During low tide, whole new worlds open up. Tide pools brimming with starfish, sea anemones, and tiny hermit crabs. Sandbars appear where there was once only water. Children run gleefully into puddles that seem to belong to another planet. The rhythm of the tide becomes the rhythm of life, playful and predictable. Of course, as with anything involving giant spinning spheres in space, things can get a little complicated. The elliptical orbits of the Moon and Earth can influence the exact timing and strength of spring, and neap tides. The Moon's orbit is not a perfect circle. And when it comes closest to Earth, called perigee, its gravitational effect is even strong. Combine a perigee moon with a spring tide and a strong storm system, and you get what's sometimes called a perigean spring tide, or colloquially, a king tide. These are the tides that turn heads and occasionally raise seawalls. And yet, even at their most dramatic, there's something deeply calming about tides. They remind us that the world runs on patterns, vast, quiet cycles that repeat with almost musical precision. The moon waxes and wanes. The sun rises and sets. And the oceans follow their lead, with patience and grace. It's easy to forget, as we go about our busy, electric lives, that we're still creatures in a celestial ballet. That the same sun that warms your skin and powers your morning coffee is also gently nudging trillions of tons of seawater across the planet. That the moon, hanging quietly above rooftops and forests, is pulling at entire oceans without making a sound. So the next time you see a full moon rise over the sea, or watch the waves slide back to reveal gleaming shells, remember that you are witnessing the pull of cosmic companions. Two great orbs, moving the waters of the earth in a duet that never ends. For example, a narrow inlet nestled between the provinces of New Brunswick and Nova Scotia. This bay is world-famous for its colossal tides, which can exceed 16 m. That's over 50 feet. Why so dramatic? Well, the bay's unique funnel-shaped channels tidal energy into a narrow, shallow area, amplifying the wave in a process not unlike a child sloshing water back and forth in a bathtub. The shape of the coastline matches the timing of the tidal wave so precisely that the water resonates, piling higher with each cycle, like pushing a swing at just the right moment. It's ocean physics with perfect rhythm. On the flip side, consider the Mediterranean Sea. It is nearly enclosed by land, connected to the Atlantic Ocean by the relatively narrow Strait of Gibraltar. This bottleneck severely restricts the flow of tidal energy into the Mediterranean. So, the tides there are minimal, often just a few centimeters. If you were to walk along the shore in Nice or Naples, you might not even notice them. The sea just doesn't have room to breathe. Then there are amphidromic points, the quiet centers of the tidal world. These are locations in the open ocean where the tide appears to stand still. Water levels here don't rise or fall significantly. Instead, The tide rotates around the point in a circular motion, like water swirling around the center of a spinning record. These rotation systems, called amphidromic systems, exist in ocean basins all over the world. If you were floating above one, sipping tea in your imaginary boat, you'd barely notice the tide at all. Meanwhile, hundreds of kilometers away, coastlines would be experiencing their daily ebb and flow like clockwork. This rotational behavior adds yet another layer of complexity. Tidal waves are influenced by the Coriolis effect, the same phenomenon that makes storms spin. As the Earth rotates, moving fluids like air and water are deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection helps give tidal waves their circular, whirlpool-like movement around amphidromic points. The whole system spins like a lazy water wheel, powered not by gears, but by gravity and the Earth's spin, and then there's the matter of resonance. Just like musical instruments vibrate at specific frequencies, so too do bodies of water. Some coastal regions are tuned, so to speak, to the frequency of the tidal forces. If the timing of the incoming tide matches the natural sloshing period of a bay or inlet, you get resonance, a condition that amplifies tidal range. It's like striking just the right note on a piano string and watching it hum to life. This is another reason why some areas see dramatic tides while others barely flutter. Let's not forget that the shape of the land above sea level matters too. A gently sloping beach will show more dramatic changes in the shoreline with each tide than a steep, rocky coastline. The same vertical change in sea level can expose hundreds of feet of beach or merely lap at the same old rock wall. This is why some beaches seem to vanish and reappear like magic, while others look more or less the same throughout the day. Tides don't just affect water level either, they influence currents too. As tidal bulges move through straits, around islands, and into estuaries, they create strong flows, sometimes powerful enough to reverse the direction of rivers. The Severn Bore in England, for example, is a tidal wave that surges upstream in the River Severn, sending brave surfers and curious spectators flocking to its muddy banks. The interaction of tides with geography also shapes marine life. Intertidal zones, the areas that are above water at low tide and underwater at high tide, are some of the most biologically rich environments on Earth. But how wide or narrow those zones are depends on how far the tide goes out. In places with large tidal ranges, entire ecosystems rise and fall with the water, adapting to dramatic daily changes in temperature, salinity, and oxygen levels. All of this is to say, the Earth isn't just a passive partner in the tidal dance. It's an active participant, shaping, distorting, and even amplifying the moon's gravitational whispers. The solid Earth may seem still and unmoving, but in reality, it's a complex stage reshaping every note of the tidal melody. So the next time you find yourself near the sea, watch how the waves trace the land. Notice where they reach and how they return. Somewhere beneath your feet is a vast, unseen landscape of mountains, valleys, and plains, guiding the ocean in ways you can't see, but the moon certainly can. Even gravity, it turns out, likes a bit of terrain. The moon has always been a loyal companion, circling us in silence, glowing with borrowed sunlight and tugging at our oceans like a patient choreographer. But the relationship hasn't always been what it is today. Like all long-term partnerships, the Earth and the moon have changed each other over time. The tides, far from being a static rhythm, have evolved across the ages. In fact, the tides we experience now are just one brief measure in a much longer song. To understand how tides have changed, we need to rewind time, not just a few centuries or millennia, but billions of years, back to when Earth was newly formed and the moon had only just been born. Likely from the debris of a massive collision between the young Earth and a Mars-sized object named Theia. The moon emerged from that chaos glowing red-hot and orbiting much closer to Earth than it does now, about 22,000 kilometers away, compared to today's comfortable 384,000 kilometers. With the moon so close, tides would have been far more extreme. The gravitational pull on our oceans was significantly stronger, resulting in tidal bulges much larger than the ones we see today. Early Earth might have seen tides hundreds of meters high, sloshing in and out with such force that coastlines may have reshaped themselves daily. The ocean would not have calmly risen and fallen, it would have surged and roared. The rapid pace of Earth's rotation back then added to the drama. A day on early Earth may have lasted only 5 or 6 hours. The faster the spin, the more frequently different regions passed through those massive tidal bulges. Imagine experiencing the full high tide to low tide cycle multiple times in a single day, a planet racing beneath a moon that loomed much larger in the sky than it does now, pulling oceans up like a puppeteer with very enthusiastic strings. But nature, as always, seeks balance. Over time, the tidal friction caused by those surging waters began to act like a cosmic brake. Every time the oceans bulged and the Earth spun beneath them, friction between the moving water and the ocean floor sapped a tiny bit of energy from Earth's rotation. That lost energy didn't just vanish, it was transferred to the moon, giving it a little boost in its orbit. As a result, the moon began slowly drifting away from Earth. It's still drifting, by the way. Today, the moon is moving away from us at a rate of about 3.8 centimeters per year, roughly the same speed your fingernails grow. Not exactly racing off into space, but over the millions of years, it adds up. The moon's increased distance weakens its gravitational influence on our oceans, gradually making tides smaller and more subdued. Meanwhile, Earth's rotation has been slowing down. Our 24-hour day is a relatively recent development in geological terms. Hundreds of millions of years ago, a day was closer to 22 hours long. And if you were to somehow fast forward a few 100 million years into the future, your grandchildren's grandchildren, times a few billion, might experience days that are 26 or even 28 hours long. It's a trade-off. As the moon drifts, Earth slows. The tides become more relaxed, less dramatic, and more like the gentle rise and fall we know today. And yet these changes are imperceptible within a human lifetime. You could sit by the sea every evening for 100 years and never notice the moon's slow departure or Earth's subtle deceleration. But the record is written in stone, literally. Ancient tidal patterns are preserved in sedimentary rock. In places like the Bay of Fundy and parts of Australia, fossilized ripple marks, layered mud, and silt laid down by ancient tides tell scientists how often the tide came in and how strong it was. Some rock layers from over 600 million years ago show 400 or more daily layers per year, compared to the 365 we now experience. This suggests that days were shorter and years were longer because Earth was spinning faster. These time-stamped sediments, along with coral growth rings and other geological clues, allow us to piece together the history of Earth's rotation and the moon's retreat. It's like reading a very slow, very patient diary written by the planet itself. But the future of tides isn't just a story of cosmic geometry. It is also tied to Earth's changing climate. As global temperatures rise, glaciers melt, and sea levels increase, the shape of coastlines will change. Estuaries may flood, islands may shrink, and new inlets may form. All of these changes will subtly alter how tides behave. In some places, tides may grow stronger, in others, weaker. The moon has made Earth what it is. Without it, Earth's axial tilt would wobble more wildly, destabilizing seasons and climates. The moon acts like a gravitational stabilizer, keeping our planet's spin relatively steady. Without it, we might not have the regular seasons or long-term climate that helped life take root and thrive. The moon gives Earth its composure, its calm. And there's something comforting, perhaps even poetic about that. That something so far away, so silent, can have such a profound, tender influence. That we are connected, quite literally, to something outside our planet. We don't just orbit the sun. We dance with the moon. This gravitational relationship, though ancient, remains deeply current. Our modern world may be filled with artificial light and city hum, but the moon's rhythm still plays on. If you walk along the beach tonight, or look out over a harbor, you'll see it. Boats rising slightly on their moorings. Wet sand drying in rippled patterns. Shorebirds probing the newly revealed shallows for one last snack before the tide comes in again. And maybe, just maybe, you'll feel it too. The slow pulse of the planet responding to something far away. The moon, ever the quiet partner, continues to shape the tides without fanfare. No engines. No schedules. just gravity, just presence. So if you ever feel disconnected, overwhelmed, or unmoored, consider the fact that every few hours, the entire ocean rises and falls, guided by a force you cannot see, but can always count on. The moon is still out there, pulling gently on the world. And the world answers. In tides, in rhythms, in whispers between moon and sea. And so, as we come to the end of our journey, we return to where we began, standing at the edge of the sea, listening to the quiet rhythm of the tides. Now, perhaps, you see them a little differently. Not just as waves rolling in and out, but as part of a grand, ancient conversation between Earth and Moon, a gravitational duet that has been playing long before we arrived, and will continue long after we're gone. We've drifted through the science, from bulging oceans and spinning Earth to moonlit fish migrations, and the slow expansion of time itself. We've visited rocky shorelines and underwater turbines, seen monks grinding grain with seawater, and crabs moonwalking their way to reproduction. We've learned that the moon, despite its quiet presence, is one of the most influential forces shaping our planet, and that the tide, for all its calm and repetition, is anything but simple. It's constant but never still, predictable but endlessly varied. A soft-spoken force with the power to shape continents, feed ecosystems, and slow the turning of the earth. And now, dear listener, as you lie back, perhaps drowsy, perhaps already floating toward dreams, I hope the tides of this story have carried you gently to the place between wakefulness and sleep. I tried not to make it too interesting. But if you're still awake, then at least you've learned something curious about the moon, the ocean, and the dance they share. If you've enjoyed this journey, I'd be quietly grateful if you'd give this video a like or tap that subscribe button for more peaceful explorations with Dodo Scientistry. It helps more than you might imagine. And before you drift off, I'd still love to know. Where in the world are you listening from? What time is it there? Leave a comment if you're feeling cozy enough to share. It's always a quiet joy to see this sleepy little community ripple across time zones and continents. Wherever you are, and whatever the hour. May your tides be calm, may your moon be bright, and may your dreams be pulled gently by the forces that have always moved the sea. Good night.